We're live.
Perfect. All right. So this is going to be our introduction to networking T-18. It's a heavy session. There's a lot of information, but it is a great introduction to what networking can be, at least from the point of view of the A+ exam. If you're looking to get into like Network Plus, you're going to have to go into even further detail with all of this information. So just a heads up for those that are brave enough to go down that route as well. As always, we have our objectives. So let's get Tiztao. Will you read our objectives for today?
Define networking, give example of networks, identify the device used in the networks, identify types of network cables connectors, recognize the most common network tools.
Perfect. Thank you, Tiztao. And our key BSMs, Jerusalem, will you take these?
It's adaptability, behavior skill, adaptability, mindset, growth mindset.
Perfect. Thank you. So we need to be very adaptable when talking about networking. If you are setting up a network for, a company, small home office, for yourself, whatever, you need to know your different options and you need to be adaptable to the needs of yourself and the client when creating these networks. And as always, we want to implement a growth mindset. Things are constantly changing and we need to grow with the technology, not push against it. All right, so what is a network? Joseph.
A network links computers for communicating and sharing information and resources. A network must provide connections, communications, services.
Perfect, thank you. So 3 things it needs to provide: connections, communications, services. So different network components. So we have our client, which is all of us right now. This is the device that the end user uses in order to access the network. So this is going to be your PCs, your laptops, your smartphones, smart TVs, whatever you're using to access the network. Then we have servers, which are devices that are set up to provide services or resources to the network. So there are a million different types of servers. We've got email servers, web servers, file servers, proxy servers. Is Bluetooth considered a client? That'll be considered a wireless technology.
Peripheral.
Yeah.
So it'd be a wireless peripheral.
Right.
Like a speaker or something like that.
Yeah. But, this is my dad's Apple Watch that he left at the house. And although it can connect through Bluetooth to his iPhone, it could also be considered a client because it's able to access the internet without the phone. So it once again, the answer is it depends, but we're going to look for the we're not searching for the exception here. Right. And then we have our network devices, and this is what creates the network itself. And so that'll be switches, routers, access points, and we'll get into the differences between all 3 of those further into the session. And finally, we have media. which is what connects the different devices. So this can be wired or wirelessly. Connections are no longer just point to point where everything has to be physically connected. Wireless is becoming more and more common in the workplace, and you'll probably end up seeing more wireless nowadays than you would wired, but you'll still have some things that you'll want to keep wired. Some examples of this are copper cabling, fiber optics, and Wi-Fi. All right, so now we have our different network topologies. What's a topology? That is a great question. Only that would be included in our slideshow. But I'm going to give it a second to see if it comes up, Julian. So, you know what, Julian, take this slide for me. We'll go ahead and get that one out of the way.
Okay. Basic network topologies definitions. Arrangement of connections between computers, also called physical topology.
Hold on 1 second. Can you read that sentence again?
Arrangement of connections between computers, also called physical topology.
Okay, so what is a topology?
An arrangement of connections between computers.
Perfect. Now tell us about mesh networks, please.
Mesh network, each node, is that how you say it? Node on the network is responsible for sending and receiving transmissions to any other node without a central point of communication. I'm gonna keep going.
Yeah, stop after a ring network, please.
Ring network. Nodes form a ring, seldom used today.
Perfect. So ring networks aren't really used anymore, but you might see one out in the wild if you're having to update someone's topology. Let's get Rachel. Will you read our last three?
For bus network, all nodes are connected in a sequential line in older topology. Star network uses a centralized device to manage traffic on the network. Hybrid network uses one or more networks to combine connections for better communication. Example, star ring, star bus.
Perfect. Thank you. So these are the different physical topologies that you will need to know of. And mesh, we're going to think of like mesh lining, or almost like a net or a spider web, where each device, each endpoint is connected to each other. There's a direct connection to each and every single node on that network. It is very expensive, but it's got a lot of redundancy. And we have our ring networks, which will look like a ring. Everything will be connected in a circle. One will be connected to another, then it will be connected to another until it forms a full ring. A bus will be a single line that the nodes will connect to. And then a star, which is it is the most common that you'll see, where everything is connected to a central device, so a switch or a hub, and they're all connected to that central device, so they're able to communicate to each other, and it's directed through that central device. And then hybrid's just going to be a combination of both, or well, any of those. Star is significantly less expensive than a mesh, yes.
We'll explain, you'll see in the next slide, and then we'll explain it a little bit better with the mesh.
So go ahead and take a picture of this, screenshot, whatever, and you can also draw it out yourself. So mesh, each device is directly connected to each and every other device. I think the calculation comes up later, or Kelly will just share it now. So this is the formula to figure out how many devices are on your mesh network. Well, to figure out how many connections you'll need, rather. So N is going to equal the number of devices you have. So we have 1, 2, 3, 4, 5, 6. So we have 6 devices on the network. If we want to make a mesh network, we're going to need to do 6 times 6 minus 1 divided by 2. So 6 minus 1 is 5. 6 times 5, 30 divided by 2. That's going to be 15 different connections. So if you go through and count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And so the number grows very, very, very quickly the more connections you have.
It becomes untenable very, very quickly.
Yes. If you just have 10 devices, that's 10 times 9, which is 90 divided by 2. That's 45 connections.
It's a lot of cable.
That's a lot of cabling. And so it's not very feasible for larger companies. Would it be harder to add a computer? Yes, it would be very difficult to add a computer to a mesh
Yes,
topology.
and that equation was for mesh, Julio. That was for the
Yes.
number of connections you would have on a mesh network.
Yeah. So we would see this more as probably implemented in a hybrid topology, where there's something that you want to be extremely redundant. So you implement a mesh topology with important systems, and then you would combine that mesh topology to maybe a star or maybe even a bus. Yes, Venkata.
Can you repeat the calculation for mesh once?
Yes. So it is N, let's see, times N minus 1. And then you're going to divide all of that by 2. And I put it in the chat. And that's how we get our mesh numbers. So our star topology, which you'll see most often, each of the devices are going to be connected to that central device. A bus topology, you'll have a single line running through, and then each of the devices are going to connect onto the line. What is the given number to do the calculation? The number of devices. So N will be however many devices that you have.
Yeah, but what is that number would be though, if that's the standard?
It's however many
Oh,
devices
they
that you.
change?
Yeah, it changes to whatever. It's just to tell you how many connections you're going to need to run the mesh network.
Okay. Earlier on the chat, I think Kelly was saying the bus was the most common. I thought
No, star
mesh was-
bus. Star bus is the most common.
Why is
because
that?
of the well, I mean, you have the bus coming into your network, so it's single points of connection coming in, and then once it gets into your network, you make a star out of it when it hits a switch. So you have a bus to get to the switch, and then from the switch becomes a star.
Okay.
So it just happens to be the most common. Like at your house, you have the connection coming in from your internet service provider from the pole. The pole hits, the connection at your house, then it hits your router. Once it hits your router, it comes in. Your router connects to everything else in your house, which becomes a star. So you have a bus coming into your house and then a star within your house. 'Cause you
Got
have a whole
it.
bunch of devices in your house connected to that one switch or router, you know, in the colloquial term.
Yes. Oh, that's what makes them common. Got it.
Yeah.
And I guess when that doesn't happen is when you go to the mesh.
Mesh would be like, you would use that in rare circumstances, although you can think of the internet as a whole as a giant mesh network.
We're not
Because it's
there.
a bunch of interconnected nodes. Do what?
Let's come back to that.
Okay, sorry.
That's too much at once.
Sorry,
We gotta
I'm
Give
getting in
them
the
just a
weeds.
minute. DW.
So the formula and
Are you asking for the formula again?
What's that star? That you just mean multiply that by?
Yeah, the asterisk just means to multiply.
All right, so it's n multiply n minus 1, then divided by 2, right?
Yep.
Okay, and that's only for the mesh, right?
Yep, only for the mesh.
Right, and that gives you the total number of connections that you need for that mesh.
Yes, exactly.
Okay, great, thank you.
All right. Venkata, did you have another question or did you just not put your hand down yet?
Oh, sorry, I'm done. Thank you.
Yeah, no problem. Right, and then we have our ring, where as you can see, it looks like a ring. Each device is connected to the next.
Do you want to talk about redundancy and point of failure first?
No,
You don't?
no. You can
Okay.
talk about it.
On the networks?
Yeah, you take that one.
You don't want to do that?
No.
All right. So on these topologies, they have their strengths and weaknesses. So we need to take into account, you know, their strengths and their weaknesses when we're building these particular networks. The major strength of the mesh is no matter where I create a break, like if I create a break right here in the network, then these computers can all still communicate with each other because they can get around that connection. Like I can get to this computer here from computer A, like going along this line and then coming up. So there is still a way for me to get around a break in communication. So the strength of the mesh network is very robust. It's very hard to bring down a mesh network. The downfall of the mesh network is it's extremely expensive to set up because of the number of connections you need to have. And it's also extremely difficult to add a device to that network. So that is something that we need to keep into account. So it has a lot of possible paths communications can take to overcome any break in the network. Now, when we're talking about a bus network, any break in the bus, the entire bus goes down. So any break, bus goes down. In a common bus topology, which is going to be different than a bus we use today. And in a common bus, they would actually have a box on either end. Typically, this was done with coaxial cable. So they would have a box on either end called a terminator. And its sole purpose was to terminate that signal. Because if that box was not there, that signal would reflect back down the line and cause data collisions, creating problems with your communications. So they would put terminators on either end. Each of these connections would tap into the coaxial cable using the B and C connectors that we talked about earlier, but we'll show those again later. And it was cheap and easy to set up, but very vulnerable if anything goes down. The ring has a similar problem. You break one link in the ring, the entire thing goes down. They still do use rings sparingly in networking, like with token ring, and sometimes in storage as a network, they'll use rings. But for the most part, they don't use it because of its vulnerability. If One goes down, everything fails, and all communication has to pass through each successive computer. So next, you have the star network. Any device on the network can go down and the network is fine, with the exception of the central node. That's the vulnerability of the star network. If the central node goes down, the entire network is down. For the most part, star is extremely effective. It's relatively inexpensive to set up. It is pretty much like, of the individuals, without including a hybrid network, it is hands down the most popular. But again, any device other than the central node can go down. The network stays intact. Unless you take out the central node, then the whole network comes down. Questions? That was a lot in a very short period of time. So questions? Yes, Rachel.
So for a wired mesh, if we're looking at this example, like how many, and it's wired, how many network interface cards would each node need?
See, that'd be tough, right? You would have to have, so in this one, what is that? 6 times 6 minus 1. Yeah, my writing is terrible.
It's 15 connections.
32. I was trying to walk them through the process. Come on.
I thought you were just trying to figure it out real quick.
15. So we would need 15 connections essentially in the back of each computer.
So each computer, 15 connections.
For
each.
this to work, you would have to have that or some other assisting device to aid in that.
That's a lot.
With every single computer. So
Yeah.
you see how that scales up. Now imagine you have a small business and 25 computers. That's a lot of cable. That's a lot of connections. It would be unmanageable. So this would be useful for very, very small amounts of computers or devices. Yes, Stephen.
What's the purpose for a terminator on a bus topology?
So what's happening is when these computers are trying to talk to each other, it's sending the signal down the lines. Trying to say, like, you got computer 1, 2, 3, 4, etc. So like, say computer 2 wants to talk to computer 4. Signal comes in and literally goes down both ways on the lines. Everybody else hears that signal. All the other NICs are like, it's like, 1, 2 saying, hey, I need to talk to 4. And then 1, 3, 5, and 6, you're like, oh, that's not for me. And they just drop it. 4 grabs it. When it hits the end of the line, there's a device there called a terminator that terminates the signal, stops the signal. Otherwise, if it's not there, it will literally reflect back down the lines. And then you have what's called a data collision, and then it gets near impossible for computers to read what's going on. So they have to stop those signals from reflecting back. All right. Yes, Karen.
So are you saying with that bus, if that terminator wasn't there and that signal goes back down the line, that whole process will repeat again where everybody will hear that the signal wants to talk to 4?
Not necessarily. But what'll happen is like the data will keep reflecting back and forth, so nobody else will be able to talk.
Okay, so
it slows the network down because you're constantly having stuff on the lines rather than it being sent once. It gets captured, it's done.
Okay. I think I got it.
So it's clogging up the communication lines.
Okay. All right.
Yes, DW.
So in a mesh network, it gives you obviously a lot of redundancy, right? You said multiple things could fail and other devices will still be able to. Then
correct.
The common bus, one thing fails and your network crashes, right? Same thing with a ring. Yeah. Same thing in a ring.
Same thing in a ring. You get a single break, everything goes down.
Right, and then
but in the ring, in the ring, this includes computers. If a computer goes down in the ring, it it comes down to, because that computer is not able to pass that message along.
Computer or a specific node in the ring?
Or no, yeah, node.
So a node, any node that goes down in the ring.
Yes, because it's not able to pass that signal along in the ring. So if that node goes down, the whole network is done.
And that's also the same thing in the common bus, right? Any node?
The bus, not necessarily. It's more about a break in the cable, because each one of these computers is tapping into the cable. They actually use what's called a vampiric connection. It's like a little spike that goes into the wire itself so that it can tap in. So if a node goes down on a bus, not so much a problem, because it's not going to interfere with the connections. It's the cable itself in the bus is the vulnerability.
Oh, okay, I get it. And then for the star network, everything's communicated off the central piece. So if that goes down, it fails. But if an individual node, if an individual node like stops working, the other ones can still communicate to the central point.
Perfect.
So everything else works, right? Okay.
Yeah, that is absolutely correct.
Thanks.
Cynthia.
So what's the purpose of the common bus topology? Because I'm thinking if there's like, I mean, I know there's evolution in network and design, but with the common bus topology, the only difference between the bus and every other one is that there's an exterminator piece. So basically, if the ring is like the Lord of the Rings for the ring network topology, if one comes down, like it's like a circle of life. Or like one comes down, there's a gap of communication, right? Like it's like it's a broken circle. So you can't. It's like saying there's a gap and you need a bridge in order for this computer to talk to this computer, right?
Correct.
But my question is with the common bus topology, and Karen brought up a good point. Is if I send information like it's just a message to Karen and she's on the other far end, but there's a gap in between number 1 and number 6, right? The communication is going back and forth, back and forth, back and forth. I mean, I shouldn't say going back and forth, back and forth, back and forth, but if there was no break, the information just be going back and forth, back and forth, back and forth. Like I'm trying to figure out like how.
I mean, eventually it would peter out, but if there was no terminators there, yes, it would continue to reflect back in.
Continue. That's what I'm trying to say.
And here's the problem. On wired networks, only one device can talk at a time. So if that signal is taking longer to dissipate, the other devices can't talk, which slows the network down drastically.
Right. That's what the whole collision, the network.
The carriers, the CSMA CD.
Right, comes into play.
Yes.
Right. And then for the star network, is the point of the central piece, which could it either be a router or network? Could it be like a combination of like network and router, or it just has to be a switch?
Typically, you would not put a router at the center of a star.
Okay, cool.
So the star would connect to the router, which would connect to the internet, which would be the bus segment of that network.
Got it. Okay. All right, that's cool.
So, because typically, I mean, with the devices we have in our houses, we have a kind of a misconception as to what exactly a router is. The devices we have in our house are multifunctional. They're routers or switches. They serve multiple things. They're wireless access points. It's like an all-in-one device, like a printer, scanner, fax machine.
Right.
So it's 3 devices combined into one, but we commonly just call it a router. But that's not typically what a router does in a network. It's a little bit different.
Right. That's the reason why I say, because there's like 3-in-1 things happening in devices nowadays. So that's why I wanted to clarify on that. And then as far as the mesh topology, the only difference well, obviously mesh is wonderful because it's like redundant, communication. But let's just say if well, I don't want to digress because that's it's part of the mesh, but I don't want to discuss it right now. I don't want to take any.
Okay, we can elaborate on some of the stuff later if you want.
Yes. Thank you.
But to your original point, the bus, why would we use something like this? This was one of the earliest types of networks, like very beginning, earliest types. This was how it started, was the common bus topology. So that's where you would see that scenario kind of come into play. Very rarely seen, and with the exception of bridging networks, it is called a bus, but it is not set up like this, which is the common bus. So but it's still considered a bus technology. Yes, Glean.
The vast majorities of these typologies are only built towards the communications, or were they built for communications and security? And if so, on the security end, which one is the most vulnerable or which one is the strongest?
I'm going to put a pin in that question until we get to security.
Okay.
So I don't want us to get too far in the weeds on that. So
Okay.
as excited as I would be to talk about that, we got to put a pin in that one until later because it is not a real quick conversation.
Okay. Understood.
So DW, did you have another question, sir?
Yeah, I'm back for more. All right, so you got everything on here, right? But then the hybrid, right? You said that the most common one would be the common bus with a star, right?
Yeah,
So
it'd be a combination of two.
So the redundancy on a hybrid, it would be faulted back to 2 points, right? Either if the cable comes in, your whole network goes down. But then at the same time, you can have individual nodes that can go down again in the star network as long as the central node doesn't go down. Right?
Correct. But here's the thing:
two critical faults there, and that's just the star and the actual.
Well, but here's the thing: if you have a star bus topology, so you have a bus coming into the network, and then that network connects to your switch, which becomes a star. If that outside piece of topology, that bus goes down, everybody still inside the star can communicate with each other.
Oh, okay.
So that internal portion of the network is still functioning, where the bus piece that takes you externally would not. So you still maintain some functionality.
Yeah, that makes perfect sense. Oh, okay. Yeah, but you won't be able to communicate outside of the internal network.
Correct.
I get it. Right. And then if the star goes down, you can still receive information, or you won't be able to receive. It doesn't work.
Well, if the star goes down, it depends on how the network is set up prior to it getting to the star. So again, that'll start getting into a little bit more complicated conversation of networking. So right now we're getting an introductory level kind of.
I'm just like doing my own like little joggings here, so I can like understand a little bit better. That's all.
I got you. I like the questions though. Jerusalem, did you have a question, ma'am?
Yes, sir. So I'm trying to understand the two, the common bus and the star network. What's their main difference?
With the common bus and the star?
Mm-hmm.
The common bus, every device along the pathway is connected, like in a line, versus the star where you have a central node, which would be your switch or your hub, that then connects out to everything else.
So how do you differentiate that when you do have them? How do you know what do you have? Like in that home?
It would be based on how the connections are made. So if I have the internet, like and
like your home.
Yeah, well, I mean, the home's kind of again a tough one because of the multifunctional devices. In enterprise situations, you're going to have distinctive routers, distinctive switches, distinctive hubs. So you're going to have these individual hardware devices where it's easier to logically see how things are set up or physically set up. So a bus might be like you have, the internet, which is poorly written, comes in. We got our little firewall right here. Then that connects to a router. And then that goes to a switch. So there's my switch. So this would be a bus. Now, where the segment connects to the switch, and I've got other nodes on that switch, that portion becomes a star.
Thank you very much.
All right, any other questions? Oh, Cynthia?
Just want to make sure when I say clear on the most common one, which is the star bus. So can you draw out what that would look like?
I just did.
Oh, that is considered a star bus?
Yeah, that was a star bus.
That was the star bus. Okay, I wasn't quite sure. Okay, I thought you were.
No problem.
Got it. Thank you. That makes sense. Thank you.
All right. Yes, Karen.
So why wouldn't that be a hybrid then?
Yes, that would be a hybrid. That was a star bus, which
Star
was a
bus.
hybrid of star and bus together.
And the bus. Okay, gotcha. Okay.
Most topologies that you'll see and implement are going to be hybrids.
And you're going to be dealing with what are considered network segments.
Yeah.
And those are going to be individual topologies within the greater network. Yes, just how.
So what's the advantage of bus topology? Advantage, disadvantage?
I'm sorry, could you repeat that one more time?
The advantage and disadvantage of bus topology.
What is the advantage of a bus topology?
Yeah.
Not a major advantage. I mean, cost is the advantage you would see on it, really. But again, it is an older topology, typically used. The most common place you see it now is connecting network segments. So you typically wouldn't see it in its traditional format, which is the old school coaxial cable, where they would literally they still call them drops today, but they literally would connect to the wire in the ceiling and they would drop down a connector from the ceiling to the computer. So you wouldn't typically see it in its historical state nowadays, almost ever. But you would use buses to connect network segments together. So that's most commonly where you see it. Does that make sense?
Yeah, so thank you.
Okay. Cynthia, did you have another question or you just had your hand up? Okay. Susan.
So just hybrids aren't like a combination of all the topologies, the best of all the topologies. Hybrids can be just different variations and combinations of the topologies. Is that
exactly?
Okay.
That is exactly correct.
Okay.
Depending on your needs, as a network engineer, you would use different types of topologies for different portions of your network. And that would be considered essentially a hybrid. So any other questions?
No, there's no more questions. We got to move on.
All right. I'm handing it back to Avery. I promise I'll be quiet for this slide.
All right. So we have two ways that we allocate our resources. We use client server, which is, as you could guess, clients and a server. All of the clients connect to a server in some way, and it shares its information amongst the different clients. So all of the information is stored in a central location. So password management, emails, files can all be stored on this central server and shared across the network instead of having to be on each individual computer. This is very handy, especially in an enterprise setting. Then we have peer-to-peer, which you can just think of it as how those topologies we were just talking about, how they connect. There aren't any servers on a peer-to-peer network. It is connected only to other clients. So everything is shared with every client on the network. So all of the passwords are stored on all of the clients. All of the files are going to be stored on all of the clients. It can get hectic pretty quickly, and peer-to-peer doesn't work well with larger networks, but it could be very useful for small networks, for like a home business or something where you don't have many clients on the network. Rule of thumb, no more than 10. If there are more than 10 on in the network, you're going to want to implement a server. Yes, Cynthia.
This is why I think this is one of the reasons why blockchain was birthed into existence, for this very reason, to become decentralized from centralization.
Yeah, and that's another big conversation that
Well, I'm gonna get into that. I just want to put it out there so people are aware.
Yeah, it's a really interesting conversation, and one that Kelly and I are both super interested in, but we'll have that at another time.
It's an ongoing one that we actually have regularly.
Yeah. All right. So types of networks by geography. So you're going to need to know the differences between all these different ANs, as we call them. So we have our PAN, which is our personal area network. And you just need to think of this, what is directly connected to your personal little network. So this is where you're going to think of Bluetooth, Firewire, USB connections, your peripherals, things that are within touch of you and your little area. That's going to be your personal area network. So my phone connected to my earbuds, that's a part of my personal area network. When I connect my phone to my car, that would be a part of that PAN. Anything that is directly connected to your little network. This is as small as we go, pretty much. It's very flexible. It can include multiple devices, but it has to be within your little area. And it's centralized around one person. Right, then we have our LANs, also known as a local area network. And I'm tired of talking. I want to hear Vincent. Take this slide for me.
Collection of computers located in a relative small area, like an office or building. All devices are connected by a common medium, allow sharing of data, peripherals, software, and storage, provides high speed and low cost. LAN topologies include bus, star, and ring.
Perfect, thank you.
Yes, sir.
So all of those topologies we were talking about, those are going to be typical for a LAN. This is your local area network. So you're going to think of your house as your LAN. All of your devices are connected to that network. My computer up here is connected to this network. The TV downstairs is connected to the network. Everything in this building is connected to this one network. So bigger than a PAN, but this is our smaller network. It provides high speed and relatively low cost. Then we have our wireless LAN, and this is where we get into our wireless mesh topology, where everything is connected wirelessly. And you're just going to think of this as a LAN, but completely wireless. It can be both public and unsecure, or private and secure. And it provides a lot of flexibility and mobility. And then we have our wireless mesh network, or woman, if you want to call it that. Susan, will you take this slide?
Wireless mesh network, WNN is a typical WLAN. Clients connect wirelessly to an access point, which then connects to another connectivity device, such as a router or switch. The key defining a factor of WMN is that it has multiple redundant connections, all using the same SSID.
Perfect. So we're going to think of our previous mesh network, where it was everything is directly connected to everything through a physical connection. It's the exact same thing except wireless, which is a lot easier to implement. It's a lot easier to connect to, my phone, my laptop, my PlayStation, all to a central router. And that's how all of the devices could be connected. You could see these in larger offices where all the computers are connecting to different access points. And then from there, the access points connect to the other access points or routers. And that's how it shares the data. All right. Then we have our MAN, or the Metropolitan Area Network. How far can that reach? It depends on how many access points you have and the quality of your routers. So you can expand
You're
it as
asking
far
for
as you
the
want.
WMN, or you're asking for the MAN, Stephen? Just to clarify.
WMN.
Okay.
Yeah, so it just kind of depends. You can make it as far as you'd like. We have our MANs, and this can cover a few city blocks to a whole city. And it can cover between a few miles, tens of miles, connect several different lands together. So this is like a central office that is also connected to a downtown office, an uptown office, the shipping warehouse office. It's spread out across the city. So just you would see this in like universities, right? Like the University of South Carolina, it's pretty much spread out all throughout downtown Columbia. It's all over the place, but it's all in the same network. So they're all connected to each other. Is there a wireless MAN? I mean, typically you're gonna have to use some wireless technology. Yes, Karen.
Yes, there is a wireless MAN. Some cities are creating entire wireless networks for the entire city. So
yeah,
that's more of a Network Plus question.
Yeah. Karen.
Okay, so would this be like hospitals that have different campuses also? Like Baptist here in Jacksonville has several different campuses, different locations.
That's a wonderful example, Karen.
Yes.
Baptist South, Baptist North, Baptist Beaches. So that is okay.
Yeah, that is a
as
wonderful
long as
example.
they're within, it gets kind of sticky when you start.
They're in the same metro area.
Okay, if they're in the same metropolitan area, then
Yeah.
yes. But if
Okay.
you have an office in California and you have an office in South Carolina, then you're getting into like a WAN, wide area network, where we're going outside of city limits.
So we don't get confused with the fact that Baptist is kind of a national thing. Think of it more like FSCJ, Karen.
Oh, okay.
Good question, Karen. Cynthia.
All right, so I think I forget who it was that brought up the wireless, the mesh. Is it like South Korea and like the smart city, how they have things like set up that's just like wireless but also connected? Because it's like a whole little city downtown, and it's like everything is like just it's not the average city. It's like a brand new city compared to what cities have been established. But I actually thought about the same thing. Is there like, I'm trying to figure out like, what does a wireless like mesh look like?
Wireless
for a city?
metropolitan
For
area
metro,
network.
yeah,
I think
like-
Philadelphia is actually setting one up where they actually have city provided network. I don't know if it's gone on live yet, but I believe Philadelphia is building one to where essentially if you live in the city, you will get at least basic internet through the wireless towers in the city, and everybody you'll have a one sign-in and password, and that basically will work all over the city.
Okay, cool.
So I believe it's Philly that is setting that up. I don't know if it's live yet, but that would be kind of how it would work.
Yeah. Okay, cool. Thank you. Yeah, smart cities are already here. Is it Stephen? Yeah, they are.
It's cool. How secure is a MAN? It depends on your security settings and you know, how they set things up. As always, it depends. They're meant to be set up securely, and that'll be, we'll get into all of that when we get into security, so I won't spend too much time. Right, then we have our WAN, our wide area network. You're going to think of the internet for this one. So how we're connecting to, how I'm able to communicate with Kelly that is all the way in Florida, even though I'm in I'm in South Carolina now, but typically in Tennessee. This is where we're able to connect to other networks on a large geographical scale, and it's a connection of multiple LANs or MANs. So it's a connection of multiple smaller networks is the best way to think about it. Right, then we have our network interface card. Leela, will you take this one?
Network interface card. Provide the physical connection between the computer's expansion bus and the network cable. Boost the digital signal from the computer. Change the data stream from widestream to narrow stream, parallel to serial conversion. Move data to and from random access memory RAM, and manage the flow of data to and from the network cable. Buffer the data from the computer.
Perfect, thank you. So our network card is how we're going to connect to our network, and then from our local area network, how we connect to a router, which connects us to the internet. So we're not thinking of our network card as how we talk to how we use the internet. We're going to think of the network card as how we get onto the network. We have to break it down into smaller steps. There are also wireless network cards, and some that will have both. My personal desktop has a wired and a wireless option with the network card, but it's how we communicate onto the network. All right, now we have MAC addresses. So Aster, will you read this one for me?
MAC addresses, MAC media access control, built-in unique identifier address in each NIC, 48 bits expressed in 12 hexadecimal characters. No two in the world have the same MAC. First 3 bytes indicate manufacturer, second 3 bytes are ID numbers. Example EOCB4E930278, also known as hardware address, physical address, adapter address, or Ethernet address.
Perfect, thank you. So our MAC address is our physical address for our devices. And so these MAC addresses are used when working with our local area networks. So how they communicate to other devices on your network, not how they communicate with devices like through the internet. That's when we get into IP addressing, and we'll do a deeper dive on that. So there, in theory, are no two identical MAC addresses, and they are represented. Let me get my annotator. So our first 3 bytes will indicate the manufacturer, so whoever made the device. The last three are going to be your identification number. And so you should be able to, you will see a question on which one of these is a valid MAC address. And so it'll be 1, 2, 3, 4, 5, 6 little sections separated by colons. The smallest that the number can be will be 0. And it's represented in hexadecimal. So hexadecimal goes from 0 to F. The largest it can be is F. So if you see anything, any letter above the letter F, it's not valid. I doubt they would throw in a negative number, but if they show you anything less than 0, that won't be right. And it also, the largest number you'll see is 9. You will definitely get a question on it. Cynthia, did you have a question or was your hand still up? Cool. Stephen.
Yeah, you said so in a MAC address, the highest letter is F, and
Yes.
the highest number would be 9.
Yes. So you won't see, you might see like, it says 78, but we're not going to think of it as 78 being one number. We're going to separate a 7 and 8.
Cool.
Good question. That definitely should clarify that. All right. Let's clear this. And so this is what you might see in a already created network. We'll get into switches, bridges, routers, repeaters. We'll get into all that in the further slides, but everything is connected in some way. So these two workstations are connected to this switch. Oh, and this file server are all connected to the switch. The switch is connected to a repeater, which connects to this workstation. The switch also connects to a bridge, so it can connect to this workstation, another file server, and some router or a router. But we'll go into more detail that just a second. So our first network device that we're going to talk about, well, I guess second if we're counting Nick, which is fair, is going to be hubs. So Glean, will you take this slide for me?
Writing things down at the same time I'm doing this. Okay. Hubs. All right. A physical gathering point for cables from NICs does not evaluate, addressing, or make decisions. Sends same message to all connected nodes. Speed to each node decreases with each node connected. Wireless models are called access points.
Perfect. Thank you. So hubs are known as dumb devices. They essentially just connect all of the devices to a central point, and that's how they communicate with each other. So if device X over here wants to connect to or send something to device Y over here, it's going to send it through the hub, and the hub is going to send the message out to everything on the network. It does not know, it knows where the message came from, so it knows not to send it back through the receiving port, but it's going to send it out through all the other ports. And then when Y sends it back to X, it's going to send it to everything else on the network. It does not remember that X sent it to Y. It's just going to send it out on every port except the receiving port. Yes, Stephen.
So it pretty much broadcasts to all the nodes.
Yeah.
Until it reaches the one that it needs to reach.
Yeah. And if you didn't guess this already, has everything is on the collision domain. If Y sends a message and X sends a message, it's going to stop the whole system. And we'll get into further detail about that later on in this session. So it's a dumb device. You should not see this anymore on a network. If you do, replace it with a switch. Cynthia, did you have a question?
Yeah, with the hub, like usually when just a small network works, it's just the whatever machine that is trying to communicate with the other devices uses a MAC address, right?
Mhm.
Does a hub? I know a hub is dumb, but does a hub? Is a hub like just like a I'm trying to use a word so that it's visually like you can remember. Like, is a hub like, let's say it doesn't have a memory, right? Like I just want to make sure I understand what a hub is like itself. I know it's not a very smart or high advanced, high tech kind of device, but it doesn't have memory. It doesn't have it doesn't have a table, right? Or does it?
Nope.
No, it doesn't.
Right?
It doesn't
Okay.
have anything. It is
Right. It just literally says, okay, A says green, and it's just gonna literally release green to all the other devices.
Yes.
And that's it, basically. That's as plain as vanilla as it can be.
Yep.
Cool.
One of the cleanest ways you can explain what a hub is, it's a party line.
A party
If anybody
line,
remembers party lines from a long time ago, a hub is a party line. So everybody on that party line gets the message. If it's not meant for you, you're supposed to ignore it. So any machine that message is not meant for, it ignores it.
You're showing our age, Kelly.
DW.
So
I'm sorry, Cynthia, you go ahead.
So for the that's never ever replicated in like other devices, correct? Like other whether it's like meaning like you know how you have wire mesh and it's redundant and stuff like that, right?
Mhm.
Like that technology, that hub repeater, it doesn't repeat itself in other designs and networks, right?
Kelly, you want to answer that one?
Can you repeat that one, please, Cynthia?
Sure. So it being that it's so dumb, right? That it doesn't really carry tables or memories or anything like that, right? But it's a very effective machine just to broadcast information quickly, right?
Yes. I mean, we still use them today for two typical types of functions because they're inexpensive. So typically you would use it to mirror reports. So like from a security standpoint, if you're using a network intrusion detection device, you would have a hub set up so that the device that's doing the detection would receive all communications. And you actually would set up a NIC card to be what's called promiscuous mode, which means it takes in every single communication and accepts it, regardless of who it's meant for. So there's a scenario where we would want to use it. Also, you can use hubs as a rudimentary repeater. Because remember, we were talking about certain lines, like lengths of cables can only go 300 feet or something like that. So you could plug in a hub and then plug the other one in, and it will duplicate that message back out for you. So you can use a hub for a rudimentary repeater. Even in small networks, though, just using a hub slows things down drastically. So like an instant way to upgrade a network is to upgrade beyond a hub. If you see hubs in the network, you replace them with other things and instantly you'll see speed increases.
Okay, thanks.
Thanks, Kelly. DW, did we answer your question?
Yeah, I was trying to get to like I was trying simplify it for myself by just using the word repeater, right? So it's like a repeater. You get one signal in, and then it repeats it all across that network.
Yep.
Okay.
Yep. It's a lot cheaper, but it is. Oh, gotta delete this. But it is much better to use a switch. It is significantly smarter. It's similar to a hub, except it evaluates the addressing and will send the packets out to where they need to go. Each network device connected to a switch is identified by their MAC address. So Kelly, myself, Safau, and Candido all work in the same office, and all of our computers are linked up to the switch. Kelly has his individual MAC address. I've got mine. Candido has his. Safau has his. And the switch takes note of which device has which MAC address. So if I want to send a message to Kelly, it knows, oh, Kelly is on line 2. I'm going to send this packet onto Kelly, and it just sends it to Kelly. And attaching more nodes does not split the speed. It's replacing hubs, and it's significantly better. It is a good device. Kelly, do we get? I think we get into the tabling later, right?
A little bit, yeah.
Okay. So essentially,
yeah, go ahead.
Essentially, it keeps track of what devices are on what ports through a table. And once a device is connected to the switch, it'll send like a quick message asking, hey, who are you? And it will add you to the table. Yes, DW. Sorry, Kelly.
No problem.
Sorry, just because we're not lining this up, Coursera, maybe we'll get you just haven't gotten to it, but the hub is at the physical layer while the switch is considered part of the network level. That kind of confused me a lot. So are you guys gonna go get into that a little bit later, or?
The hub, well, I mean, yeah, I mean, I can talk about that here in a minute.
We have a whole session that we'll go into what devices are on what part
what
of the
layers of the technology.
Yeah, let's not do that yet.
That's Monday.
That's Monday. That's a big lesson. He thought this one was bad. Wait till Monday.
Sorry, Hell Week has started, everyone, just so you're aware.
Yes. All right. Do I have this one, or is this yours, Kelly?
I think this is handed to me.
All right.
All right. Do we want to take like a 5-minute brain break before we dive into the next group?
That's a good idea. 5-minute break.
All right, it's 5 minutes. Let's return here at 2:50. Okay, so we're talking about the hub. What'd you say?
Gotta share your screen.
Oh man, I thought this would be more exciting if I just described what I saw. Sharing is caring. All right, so originally we were talking about the hub. Dumb device, operates on layer 1. Anything that comes in goes out all the different ports. Just basically shouts your business out to everybody and just relies upon the good nature of the many nicks out there listening, going, nope, not for me, and doesn't pay attention. Then we move on to switches. operates on layer 2, data link layer, pays attention to MAC addresses, and it's going to make those communications directly utilizing MAC addresses. Now we're getting into the next type, which is the bridge. The bridge is essentially a connector between two physically dissimilar networks. Now, what do they mean by that? So physically dissimilar, this would be like wireless to wired. That WAP, the wireless access point, the WAP, that is a bridge. It's taking your wireless communication, taking it, converting it to a wired technology and sending it along the network. That is a bridge. It's not the only kind. We could have one going from coaxial to Ethernet. If you have cable internet at your house, the device that you affectionately call your router also is a bridge. It's bridging the technology from coaxial to Wi-Fi and to Ethernet if you so choose. So it is connecting physically dissimilar networks. Fiber optic to wire or to cable, that would need a bridge in order to make it so those two different types of physical networks can communicate. So it's converting the signal in some manner, changing how the communication is taking place. It bridges those two different networks. Typically, you would only have like maybe one in and out on a bridge. It's kind of a pass-through. It's like a converter. Yes, it can go the other way too. It can go from wired to wireless. That's how you get your internet. So you have the wired communication comes into the WAP. The WAP changes it to a wireless signal, sends it to you. You receive that information. You reply to it or to a website, and it sends that wireless back. It converts it from wireless back to wired and sends it back out to the internet. So communication can go both ways. It is bridging two physically dissimilar networks. Then we have gateways, which is essentially is a connector between two logically dissimilar networks. Well, what do we mean by logically dissimilar? We mean the difference between a bus and a star. So at the end of that bus, before it can become a star, you would have something like a router. The router would connect the two logically dissimilar networks. The bus has one essentially logical way that it communicates, and then the star has another. So it is communicating to two logically dissimilar networks. The bridge is the physical. The gateway, which is typically a router, is the logical. And the logical topologies is the bus, star, mesh, ring. So in order to change from one of those to the other, you have to have a gateway to make that conversion. And then if you're going from communicating on one type of technology, be it unshielded twisted pair, which is your typical Ethernet, to coaxial, you would need a bridge in order to convert technologies. Questions? In a sense, you could say it is duplex, Karen, because the communication is going both ways. What question do you have, Julian? Okay, gateway. So you have, remember how we were just talking about the bus, the ring, the star, and the mesh, right? Those are what are considered logical networks. Those are logical topologies. They have a certain way of communicating. If I want to change over from a star to a bus, I need some form of a gateway so that it can change that communication type. And that is the gateway, which typically when we refer to a gateway, we mean a router.
So a gateway is like a physical device.
Yes, exactly. A gateway is a physical device. It is a network device. Most common gateway is a router.
Okay.
I wish they would have just put router there to make life a lot easier, but it is considered a gateway. So if I'm in my star network and I want to go out and talk to the internet, I have to get out my gateway, which is my router. You might have seen it when you're putting in like your network stuff when you first put a computer. It'll have a slot there for your gateway. That gateway is your router. That's that separator between your network and the outside network. Yes, DW.
What's the actual term for the bridge device? What's like
a bridge? That's the term.
So, but I'm saying like a bridge from optic to Ethernet will be the same bridge as from Ethernet to Ethernet wireless.
Well, the device itself would be called a bridge, but we may have a specific term for it, like WAP, wireless access point. That is a bridge from wireless to wired. So as far as network device is concerned, that is considered a bridge device, but we call them wireless access points. So if you have a manufacturer that makes it, they may have a specific name for it. Yes, Cynthia.
Even though that routers are the logical separators between like the internal network and the outer network of things.
Not only that, but that is the main one, yes.
Right. But and I'm referring this to the gateway so that I'm actually clear on this. So the router is really the physical device that separates, or actually that bridges the two. But what makes it different than the bridge is that the gateway, if I got this correctly, is that if you have like a local LAN, like just a regular home little business, and then you want to connect to like another business, that's
yeah, you would have like a star in your network connected to that router, and that router would connect you to the internet, which would then connect you to another router on the other end to get internally into their network.
Got it. Thank you. That's what I wanted to.
Now,
so it wouldn't really even matter. Like, let's say, even though I'm tiny, let's say I want to get into like a bigger network, like a MAN, let's just say, right? Like a metro, right? That's also could be considered. I would just have to be connected through whatever access points or whatever. Let me not go too far, but that would also be considered a gateway. So that if I'm here and I'm working remotely, but I'm working for a city in another state, that whole connection would be considered a gateway, because it's
the connection between you and the other part.
Right, that's what I'm saying. Right.
So say like I work for Skynet, and I'm in the 3rd floor accounting, and I want to talk to HR on the 5th floor. So the 3rd floor has its own, little star network that's set up. It would go to the router. The router would say, okay, you need to talk to the router on the 5th floor, send it up to the 5th floor. That router would say, yep, that's for me. Send it internally into their star network on the 5th floor.
Okay, that makes sense. Thank you.
So the gateway is how you get out of your local topology.
Got it. Thank you. That's what I needed to see. Like, that's your way out. Okay, cool.
Yeah. Yes, Karen.
Okay, so my question is, my router has a WAP button on it. What does that mean?
Is it a WAP or a WPS?
Let me go check real quick. Oh, WPS. It's WPS.
We will get into WPS.
Okay. Okay.
We will get into WPS. That is a great initial idea, but probably one of the greatest security risks to any network.
Oh, okay, cool.
So we'll get into that. Don't worry. So, okay, bridges, gateways, switches, and hubs. All hearts and minds are clear. At least basic definitional understanding of what they are, what they do. All right. Next. A little more detail on routers. So a router makes forwarding decisions based off of logical network addresses or IP addresses. So based on the IP address, anything that is received by the switch internally that it does not recognize, it typically will send it to the gateway, or it will be packaged in such a way that it's going to go through the gateway out of the network. That router will make a forwarding decision, say, yep, this isn't meant to stay internal into the network. I need to forward this on. And it communicates with other routers. And it will forward those decisions on based on internal, routing maps essentially that it has. That's beyond the scope of this course, but essentially based off the IP address, it's making decisions on whether it stays internally in the network or it goes out. DSL stands for Digital Subscriber Line. All right. So the router itself routes packets or chunks of data between sub networks. So it'll have a list, and because the way the entire internet works is essentially an interconnection of tons of routers. So your router, even though you may not be using it, may be used in forwarding decisions of other communications. So like the router closest to it might go, yep, the fastest way we can get there is passing it through Karen's router. So it hits Karen's router, then it moves on even further. So it's an interconnection of routers, and based on how they talk to each other, determines how it's going to send those packets out through the network. Now, this one right here, this is, kind of typical what you would see in your house. So this one is rather old, but this would be a router like you would see in your house. Now, the ones that they have in enterprise environments, really big. They are significantly different, much more robust, and wouldn't even have as many connections as yours does, because remember, yours serves it wears multiple hats. It's a router, it's a switch, it's a wireless access point, it's a bridge. So it's like all of these things in one, where one you would use in a enterprise environment is strictly a router. That is its sole job, and it does it really well. So, but the main takeaways, it basically makes forwarding decisions of packets of data based off of the IP address, which is like the street address for your computer. So once it has that, it's, and you tell it which computer you want to talk to based on that other IP address, it forwards that information on to them automatically. Quote Mike Myers. All right. Yes, Glenn.
IP addresses and MAC addresses are not the same. The MAC address is kind of like the physical address for your system, meaning like the house is 123 Anywhere Street.
Yeah.
And the IP address could be Texas, Jersey, Florida, or something along that nature.
Well, what it would be is kind of like the IP address, especially the way that the IP addresses work right now. The IP address might be your street address, so that would be 123 Main Street, and the MAC address may be Glean in that household. Because interestingly enough, once it gets internally in the network, your switches and stuff are using MAC addresses to communicate internally. The IPs typically are on the outside. But we're going to talk more about that in TCP/IP. It may shock you to know that we actually ran out of IP addresses back in like 1997. Like that long ago that we ran out of IP addresses. So we've been using a lot of internet magic to kind of keep things running until we could get new protocols in place and start transferring over, which we're in a transitionary period now. So yeah, back in 97, ran out of close to late 90s, we ran out of all IP addresses. We were done. So we had to start doing some kind of creative thinking to get around those problems. All right, questions so far? Yes, Melinda, that is why we have IPv6. All right. Devices on a network, firewalls. So Steve kind of picked up on this. This can actually be software on an individual computer, or it can be a physical hardware device that you route all traffic through. Typically, you want to place a physical firewall on an edge of your network so that all communications must pass through it. Now, firewalls can have multiple interfaces, allowing for varying levels of security, and it is significantly better than software. Does anybody remember what exactly, or what typically a firewall uses to determine whether or not to allow communication through? Yes, Cynthia.
The access control list.
Excellent. The access control list. Can you give me a basic description of what that is?
So basically, if I'm the administrator and I want certain, I'll put in like certain IP addresses that should be able to communicate back and forth. And if I don't want a particular, if I have an employee that I don't want them to go to a specific website, I can put that as well to restrict internet access between internal and external communications in the network.
There you go. So an access control list is basically a set of rules to say what can pass through, what cannot. We have essentially what is called a packet filtering firewall, which is what is considered a stateless firewall. And what it's going to do is based on rules like where it's going and sometimes what information is being transmitted. It's going to basically scan all of the packets going through based on the type of information or to where, you know, who they're communicating with, and can shut down anything that it deems it doesn't want to let through. So like if you were in the research, you know, R&D department and company Y paid you 10 million bucks for the research and you wanted to kind of send it out through the network, the firewall would look and say, proprietary information, we're not letting it pass, and shut it down, and then possibly alert the network administrator. So it uses this access control list, which can either be what's called a whitelist, which a whitelist means only these things are allowed. Anything else that is not on this list is to be shut down. As a network administrator, that's the hardest one to set up because you will be updating this thing constantly. And then the other is a blacklist, which basically means everything is permissible except the things that are on this list. Slightly lower in security, but significantly easier to set up if you're a network administrator. The other type we have is a stateful firewall. What it is doing, it is paying attention to the state of the conversation that's being had. So what it's looking for is the only conversations that would be allowed outside the network would be conversations that started from inside. So if I'm on site at, you know, Skynet, and I want to talk to, you know, our good buddies over at Google, you know, I would have to say, hey, Google, I want to talk to you. And then the firewall would allow Google to make that communication back to me. Now, if I was at Google and I wanted to start a conversation, or they wanted to start a conversation with me at Skynet, they would try to send that communication to me, but the firewall would block it because the state of the conversation had not been created by me internally. So that is a stateful firewall. It's paying attention to the state of the conversation. And they assume once the conversation has begun, all communications at that point are consensual. So it lets all communication continue. It just has to originate from inside. I guess you could say that, Jessica. It's kind of like a chaperone. So does that make sense? You have the packet filtering firewall, which examines every single packet to make sure it upholds the list of rules you have in place. And you have the stateful firewall that's paying attention to the state of the conversation. So as long as that conversation is going on, it's not going to block it, but the conversation must initiate from somebody inside the organization. All right. We will now take a breather and start talking about network physical communication. So, ways we can talk, we have a whole T session, completely surrounding just wireless. So we're not really going to be talking about wireless in this one. This is going to be physical communication methods, wired communication, essentially. First one on the docket is coaxial. Essentially, it's broken up. You have the center conductor, which is the copper cable in the middle. They have a dielectric core that kind of protects it. There is a braided shield around it that gives it pretty decent resistance to EMI, which is electromagnetic interference. And then you have the jacket that goes over it, kind of protects everything. So there's a few different types we need to be aware of. You have the RG59, which is used for short distance applications. This is typically internal networking. You have the RG58, which is typically your old school cable TV type connection. And then you have the RG6, which is much thicker, much harder to bend, much more robust cable. And that's used by the cable companies to connect the homes to the distribution network. So that's the stuff that's outside on the telephone poles and all that stuff. That is your RG6. The RG59, RG58 would be from the pole or internally in the house, essentially, or the office. Ohms.
75.
Yeah, 75 and 50 ohms. It's like OHMS, I believe. It's a measure of current. All right. So that is your coaxial cable. Here are our two types of connectors you will see on the end of those cables, which we have mentioned before in the T session that's near and dear to all of our hearts, cables and connectors. We have our B and C connector, bayonet Neil Councilman. You can kind of see these little notches right here where you'd have that little T piece that would go in and then twist and lock into place. This is typically what you would see in networks. And then you have your F type connector right here, where you can see the threaded screw on it. And that is typically what you would see for cable TV, things like that. What's passing through the copper wire? Ones and zeros. It's a really fancy Morse code, on and off.
Now I was asking that because like in fiber, it's light, but I remember through the copper, it's electricity.
Yeah. Uses current to create those ones and zeros. All right. So 10-base-2, that is the naming standard for the Ethernet network. You will see this type of nomenclature come up a lot. Base is short for baseband. 10 is how many megabits per second can travel on it. And 2 would identify it as the BNC type connector. So 10 base 2 will let you know that it is a coaxial cable that can push 10 megabits per second. Yes, Leela.
You said the 10 is how many mega what?
Megabits per second, small b.
Okay, thank you.
And you'll typically, when you're talking about internet, it's like that, big M, small b. When you're talking about storage, it's typically big M, big B, megabytes. All right, shielded twisted pair, or STP cable. This is pretty similar to most Ethernet cables you have, although the majority that you probably have at your house and a lot of times in offices would be what is considered unshielded, which we will get to. The shielded twisted pair, it is more expensive. It is harder to work with. It has these 8 wires in it that are like twisted together, as you can see. And then they have a foil wrapped around those wires to try to avoid or minimize any electromagnetic interference. So this is what you would see typically with your RJ45 connectors on it. So it has 8 pieces of wire that are all twisted together in patterns like this. Now, it is essentially, yeah, tinfoil. And then they typically will have a Kevlar strip running in alongside it as well. So can anybody tell me, why do they twist the wires together? Why not just run them straight? Wouldn't it be easier? Be like a thin flat cable, run them straight, you're good to go. Does anybody think about why they twist them like that? Seems like that's a lot more work. Cynthia.
Is it the way that?
Oh, Karen, go ahead. No, go ahead.
Oh, no. Is it because of the way that they'll send the messages, send and receive the information?
Well, I mean, but that wouldn't really change even if it was straight, right? Like if they just push them straight through, but this seems like a lot of extra work. They're twisting the cables together. Like they have these 2 yellow cables twisted together, these 2 blue, these 2 brown, and these 2 green. They're all twisted together.
I'm not sure then.
Okay. Cynthia?
It actually helps avoid the electromagnetic interference when the electrical pulses are going through. So it actually it's almost like a buffer. So
okay.
It's like saying if you have a direct wire and it's live, that means it's just pure current going through. But if you have it twisted, it helps with the electromagnetic interference and communication between one device to another device using the twisted pair.
Okay, well, we're starting to knock on the right door. Lean?
But I thought that these colored wires had a specific order in order to feed to certain devices or to be able to communicate back and forth onto them.
Oh, you're getting a couple slides ahead of us.
At least that's what I remember. But that's what I remember, that these specifically, they were colored to communicate to certain devices in a certain manner. Or like you have to get them set before you can crimp them and never to place them in.
That is absolutely correct. You do need to get them set before you crimp them, but we'll get to wire standards here in just a little bit on that. DW.
Is it to stop, I can't think of the term, but when it jumps from one line to the other.
That's exactly what it is.
Okay, so
you think of the term?
Crosstalk.
Crosstalk. There you go. Great job.
Yeah,
Great job.
Yeah, that was it. Awesome. Thank you.
they twist the wires together to prevent crosstalk. So what's happening is when these wires are twisted like this, they're always touching each other at a right angle. So the current isn't flowing parallel and allow for easy crosstalk. So they're not running side by side, they're crossing over. So they're always sitting at a right angle from each other. So they do that, and that allows for the wires to have much longer runs and not have a degrading signal. So the crosstalk is the whole reason for why they twist the pairs of wires together. So in this particular one, like I said, this is a shielded twisted pair. This has the tin foil on it underneath the cladding to kind of help add to that to prevent external electromagnetic interference from, messing up your data. Here, this is typically the most common one you'll come across, which is UTP, or unshielded twisted pair, no foil. So these tend to be the least expensive. They're the easiest for network engineers to work on. So if there is no distinct reason to actually have the shielding, a lot of times they will opt not to use it, especially on things like patch cables and stuff like that. Now, if you're working in manufacturing and something like that, where you have a lot of machinery moving around and a lot of stuff that will create that electromagnetic interference, you're going to want shielded cables. Otherwise, it'll be near impossible to have your network devices talking, because they will have so much interference between them. So most common cable used in LANs because it is the least expensive and the easiest to work with. But again, you can see that tight twisting of each of these cables. And here are the fun categories that we have for this. You might have heard somebody say like a Cat 5, Cat 6, Cat 6A, Cat 7. All of these numbers have very specific meanings. They will tell you what is the maximum length you can run that cable before you start getting what's called signal attenuation, or a degrading of the signal. And you would need something like a repeater in order for the signal to continue on any further. So 100 megs or 100 meters, maximum length, or 300 feet for the majority of them. Then your speeds vary too. Cat 3, 10 megabits per second. And then it quickly jumps up to 16, then 100, big leap to Cat 5. That was such a big deal in the industry when we went to Cat 5. And then Cat 5 to Cat 5e. That's a 10x jump. It can run up now to 1 gigabit per second. Cat 5e to Cat 6, 10x again, 10 gigabits per second. Now, the difference between 6 and 6A is actually the distance. 6E could run at 55, or 6 can run at 55. 6E allowed back to 100. It is unfortunately mismarked here. And then category 7, still gigabit Ethernet, but category 7 is completely shielded. So the standard for 7 requires all of it to be shielded, including the connectors. So the RJ45s themselves are shielded too. They have a very chunky look to them. They have a metallic shielding around the actual connectors for your network as well. Do we need to know this? Is this important? Yes, it is. So I would suggest taking a screenshot of this.
Hey, Kelly, I'm sorry. Can you just reconfirm? You said it was Cat 6E that was listed incorrectly. Can you just verify what section that was again?
No, category 6 had a 55 meter length. After 55 meters, the speed drastically dropped off. So maximum length was considered to be 55 for the 10 gigabit speed. 6A corrected that issue. You got the 10 gigabits per second all the way up to 100 meters.
Gotcha. Thank you.
Okay, so this is for unshielded twisted pairs, right?
Yes, I mean you can have shielded cables like this, But the standard is essentially based off of unshielded twisted pair, yes.
And in this, and so only category 7 is shielded in this list.
Yes, category 7 is a shielded classification. It's a shielded category.
And you said in that category, it's even up to even the connector is shielded as well.
Yeah, the connectors will have you'll have metal shielded connectors too on top of that. So you couldn't use a standard connector with that. Otherwise, you would actually lose the benefit of it, because if you're in heavy manufacturing, it would still interfere with it, even at that small gap where you would have that connector. That help this time? They make note of it over here, but it's confusing. All right. Questions, comments, concerns, complaints, headaches? It's brain food, Jessica. All right. Twisted pair connectors. We have 2 different types of connectors for twisted pair. We have the one we are most familiar with now, which is our RJ45. That is our Ethernet connector. It has the 8 pins, and you see the cables coming into it here, allowing it to terminate with that type of connector. Now, the old school POTS connector, the RJ11, has 2 to 4 pins typically. And towards the end of its life cycle, they discovered the twisted pairs, allowing to decrease the amount of attenuation or static. Those of us, when we were kids, if we actually had phones in our house, that actually had wires attached to them, that kind of fun stuff. When we talked on them, when we talked to people long distances away, there used to be a lot of static on the lines. And the longer distance you try to talk, the harder it was to hear people. That was because of the attenuation on the lines. The static was because they weren't shielding or twisting the wires. Once they started twisting the wires, all that stuff got a lot cleaner, and we were able to hear each other from long distances now. Now we don't even need wires. All right, any questions on this one? Yes, payphones essentially did use RJ11 underneath that really thick steel covering over the wires that they had. And if you were clever enough, for the last wave of them, you actually could put coins into one and record the tones being made, because the payphone would send a tone over the line saying that it received money. So you could put the money in and record the tones, hang up the phone, get your money back, then pick up the phone, play the tones over the payphone, and then you could talk however long you wanted. And whenever it asked for money, you just played the tones again. I heard from a friend. All right. Gleen's favorite slide. We had to get to it. So wiring standards, because these wires have to go into these connectors in a very specific order in order to be able to communicate with each other. You have two different standards that we have to know. There's the T568A and the T568B. Now, this would be if you were looking at the bottom of your, like if you have your cable right here. I can get close enough without it thinking it's background. Yeah, so the little tab on the top, based off this, the little tab on the top is on the back. So you're actually looking at it from the very bottom of the connector. And there you go. And you can see the colors. Oh, the colors of each wire. So I can look at this one. And this one is a T568B, just based off the wiring. Yes, Jessica.
I'm just curious, are these things like handmade or like machine made? I'm just curious.
Typically a machine makes them, but as a network engineer, you might get the personal joy of making them yourself. We actually had a guy who did this stuff pretty regularly in my cohort when we were on site, and he brought a whole bunch of cable in and like a big old bag of connectors, and we literally just sat there one afternoon learning how to make cables.
Oh, wow. Thank you.
So, gosh, is there some sort of way that we can look at this so it's easy to remember? Is there some sort of mnemonic or memory device we have? Yes, we got you covered. So for T568A, say the trees to the sky, that's the green, brown to the ground, brown goes on the bottom. And the river runs on a sunny day. So the river runs in the middle, and then you have the orange in between it. Always remember, the standards always go stripe, no stripe, stripe, no stripe, stripe, no stripe, stripe, no stripe. That pattern never changes. So it always alternates between stripes and no stripes. So 568A, trees to the sky, gives you the green, brown to the ground, river runs between a sunny day. So the orange is split in this particular one. T568B, this is the most common one being used, also the easiest mnemonic to remember because it makes more sense. Sun to the sky, see the orange going to the sky, brown to the ground, and the river runs between the trees or the valley or whatever. So you would have green stripe green, orange stripe, blue, blue stripe orange, and then brown stripe brown. Please take a picture of this slide. Remember these memory devices. We will be practicing this order or these orders quite a bit on Jamboards to get to kind of ingrain it in your memory.
I've got a pro tip, Kelly.
Avery's got a pro tip because his mind works differently than mine.
Yeah,
I only do amateur tips.
All right. So first things first, you only have to memorize one of these. So whichever one is easier for you to remember, that's the one you're going to focus on. So for me, I like T568B because I like to imagine the sun in the sky. It feels like a better order for myself. So you'll notice that brown and blue are the same on both of these. So your B's are always going to stay the same. Your blue and your brown do not change, no matter which standard you're using. The only thing that's going to change are your green and your orange for these. So you're going to pick the one that you want to memorize. So if you're doing B, you know you're going to do stripe, no stripe, stripe, no stripe, stripe, no stripe, stripe, no stripe. It's going to be orange into green. Our blue stays the same, solid green, and then our brown. So orange, white, orange, orange, green, blue, orange, green, or white, orange, orange, white, green, blue, white, blue, green, white, brown, brown. Once you've got that memorized, you're only going to switch your orange and your green for the other one. And that's it.
Simple, right?
It really is. Give it an afternoon.
Yeah, you'll
just
pick it up quicker than you think.
It's scary at first, but just take an afternoon, memorize one, and then you can just flip your colors for the others. Julian.
I have a question. Will we have to memorize exactly in what color order these cables are set up in, or should we just memorize, okay, I know the B is the one with the orange on top, and then A is the one with the green on top?
No, you need to know the exact order.
Because they may ask you, they may show it to you out of order.
It's possible you'll be asked to make a cable.
Yeah.
Where they'll give you the different colors and you put it in yourself.
Also, if you have a network cable at your house, look at the bottom of the cable and see which standard you have. Do you have an A cable or a B? So if you have a cable, just pull it out, look at it. You should be able to see the colors through the connector, and you can determine whether you have a standard A or standard B. Also, on the cables, to make our life easier, because not all cables are created equal, they actually stamp on the side of the cable. So I can find it here. Turn off my background here for a second so I can show you. All right, so let me stop share. So on the cable itself, so I can get it clear enough where you can see it. So here it says UTP Cat 5E. Scan along a little bit more. You can see 568B. Tells me exactly what standard is on there. So everybody see that? UTP Cat 5E 568B. They type these standards pretty much on almost all cables.
And all this time, Kelly, I thought that stuff was useless, but good to know. Thank you, because I've seen it. That's something I've noticed. It was like, why is this even here? Thanks for sharing. That was really cool.
So try to bring everything full circle when we can.
I'm gonna go and brag to my family members, like, let me see what kind of cord that is. They gotta be like, well, actually, what you have is, oh yeah.
Oh, this is a Cat 3. It's a bad cable. You don't want this. Now, this is very important. Cables are more important than you think. So if you have switches set up in your office or what have you, and say a cable goes bad, a cable gets broken, and you go and you pull that cable out, and then you just snatch a patch cable out, first one you see, and you plug it in without paying attention to what Cat rating it is, you can cripple an entire network. You can bring an entire network down to its knees because you have just created a bottleneck. If I throw a Cat 3 cable in on a Cat 6A network, all of a sudden everything can only talk as fast as the slowest device. So it slows everything down. So you can bring down an entire network by just using one of the wrong cables. So pay attention to your cables. They are very important. Although spanning tree protocol can kind of help you there, but again, beyond the scope of this course. All right, any questions with regards to wire standards? Cynthia, did you have another question, or is your hand just still up? Nope, she's not there. Over. Did you have a question, Cynthia?
No, I was putting back my toolkit. I was like, I have the same cable you do, but it's just in green, but it's like a Cat 5e. And so I hadn't seen it in a little bit, but I was like, I took it out, and I was actually practicing a while back on how to use the crimper and put in the wires. And it's actually fairly easy. Like once you have the actual physical wires in front of you and you start to do it, it's pretty neat. Like you're like, yeah, look at this. I just created a wire and I can now connect my whatever it is I want to connect. It's pretty neat.
So like when I was talking about updating my network at my house, because the wireless network, it's terrible because the Wi-Fi routers on one side of the house, my office is on the other, horrible connections. And I was trying to go wired. And so I went and bought a spool of cable. I was like, you know what, rather than paying somebody to come out here and do it, I know how to do this stuff. I'll just buy a spool, make my own cables. Everything works great and works pretty good. So once you know how to do that stuff, you don't necessarily need to bring somebody in to do it. You can do it yourself. And it's, yeah, it is not that hard, but it can be frustrating. And you do need to be sure to test your cables after you make them. Yes, Julia.
Yeah, I'm just still a little confused as to why there's two types of standards. Like is one used for something and the other one used for another?
We will get into that.
Okay.
You just got a couple slides ahead of me, but this is like two different wiring standards you can have. We will get into why there are two different ones. Good question. No, it's not just because we want to stress you out for the exam. All right. Sure, this one is familiar to some of us, if we remember. There is the plenum cable. They love asking about plenum. In fact, it is likely you will get more than one question where the answer is plenum. Typical unshielded twisted pair, the coating that goes around the wire is made out of PVC. PVC is extremely toxic when burned. So it's very bad, you know, for your lungs and all that stuff if it burns. So if you're going to be running any kind of networking cable through a drop ceiling, sometimes they'll run them through the HVAC ducts so that they don't have to, you know, create new holes or anything like that. So sometimes they'll run it through HVAC ducts. Anytime you do something like that through the drop ceilings or wherever it's going to interact with the air that people are breathing, you have to use plenum cable in case there is a fire. The plenum cable itself is fire retardant. Like you can actually sit there with a blowtorch on this stuff and it will barely smolder. It'll melt and smolder, but it won't burn. So you don't have to worry about poisonous gas if a fire starts up in the building. So anytime you're hearing about drop ceilings, HVAC, or fire retardant, your mind should instantly go to plenum. There is no other answer. We're going to repeat one more time. Plenum is to prevent poisonous gas in burnings used in drop ceilings and HVAC ducts. I hope I stressed that enough. All right.
All right, Kelly.
Yes.
What are the things that are actually poisonous? Like just the regular twisted pair cable?
Yes, the shielded twisted pair and the regular twisted pair. The coating that the black coating that they have around the cables itself is they make it out of PVC. PVC, when burned, creates toxic chemicals. So they have a special type of cable that has this coating, and the coating itself is flame retardant. It doesn't burn or create toxic gas. It just kind of smolders and melts. So it's much safer to use in drop ceilings and AC units where there would be an air exchange between us and the cabling.
Daddy, I made gingerbread house today.
All right, sorry about that. All right, so our next type of communication that we're going to be using, fiber optic. So it uses light instead of electricity, which means, woohoo, it is immune to electromagnetic interference. Now, it is potentially possible to have a magnet strong enough to interfere with light. But good gravy, you would not want to be anywhere near something like that. So it is highly, highly unlikely. So for, predominant use, it is immune to EMI. No, not even MRI machines would be strong enough to interfere with light. So it'd have to be much stronger than that. Like creating gravity wells kind of thing. All right. Also, the light in it is injected by one of two things. It's either a laser or an LED, or light emitting diode. Fiber optic is somewhat flexible. There actually is a measurement to determine how much you can actually bend a fiber optic over a certain distance before it will actually break. So yes, Cynthia.
Yeah, with fiber optics, you gotta be careful because like when you're cutting it and you have to put it in, like you have to shave it. It's very, believe it or not, it's kind of sensitive, even though I think it's more delicate.
Yes.
Than the coaxial.
Oh, extremely so.
Yeah.
There are specialists who focus specifically on dealing with fiber optics.
Yeah.
And they make really good money. This back in the late 90s, early 2000s, when I was in school, I originally was studying engineering. On a job that we were kind of observing, they broke a fiber optic line. It was $2,000 a minute until they got it repaired. This is back in the late 90s, early 2000s. $2,000 a minute is what the construction company was being charged until they could have that line repaired. Now, how much do you think they would be willing to pay for somebody to come out and fix that line right now? A lot of money.
Especially because they're in data centers. Usually, like they usually invest fiber optics in data centers because you have to move information a lot quicker than if it's just like at home, let's per se.
Well, I mean, in an enterprise environment, typically you're using fiber optics in your storage attached network where you need extremely fast communication, or if you're dealing with large mainframes and supercomputers and stuff like that. So it is significantly more expensive, but big benefit. They can go much longer distance and carry a heck of a lot more data. Did you have another question, Cynthia, or did you bring your head down and back up? Okay. So you have two specific categories. You have MMF and SMF. Most fiber optics look about the same. You have the outer jacket. You have a piece that literally all it is there to do is to provide strength to that cable itself. You have the coating, and then there's an outer cladding, and then you have the optic core where the light would be transmitted down. So MMF, or multi-mode fiber, this is very high speed at a minimum distance. The way it achieves this speed is that it is using different colored lights to shoot data down the line. So it's able to use multiple different LEDs at different light spectrums to create essentially multiple communications down that line. You have single mode fiber, high speeds over great distances. Costs are higher, and it typically uses a laser, so it goes a lot further. Here is kind of a look at it. So multi-mode, each one of these lines going in would be a different color LED, and they are all pushed down that line. So you can have multiple communications at one time. And it kind of gives you the idea about the cladding, which will reflect the light internally back in. And because of so much reflection inside, it shortens the distance it's capable of running. Single mode, single laser, straight down the middle, allowing it for high speed over a very long distance. How long of a distance, you may ask? Typically, the cores are about the same. They had them difference in size because of just ease of visual representation. All right, so how far will they go? Well, great question. So multi-mode, your maximum is about 2 kilometers. Yes, you do want to take a picture of this. Single mode, between 2 and 10 kilometers are your typical runs. And we see the return of the base. Easy way to remember it. So remember the number in the front tells you how many gigabits per or megabits per second. So 1,000 megabits per second would actually be 1 gigabit. And then you have a 10G base here, LR for long range. LX, what is it? Long extended. So just remember the L's will give you the long distance ones. Your short distance, you have SX, SR, and FX. So multi-mode, shorter distances between 300 meters to 2 kilometers, single mode, 2 kilometers to 10 kilometers. Well, we also got to connect these to our, network devices. So we have a nice variety of connectors that we have to know. So we have our straight tip, or ST, and then it has a straight piece that comes out that will generally fit into and uses a BNC connector to twist and lock. So ST for straight tip. Not to be confused with your SC, which is a square connector. It has a very square face on it. And then you have your LC, which just kind of makes an L. If you can remember that, it has that fun little clip on the end of it. So LC, which is your Lucent connector. And then the oddball of the group that has 2 strands running through a single connector, which is the MTRJ. This is also what is considered a small form factor, because this connector here is going to be smaller than these other 3. So it's a small form factor. It's 2 wires in one. You can see the 2 little nubs sticking out here. So it's 2 fiber optic connectors in one, and that is your MTRJ. Sitting there asking yourself, will we get a chance to practice this? Yes, I promise you will. Jamboard has you covered.
You're making a lot of promises.
I'm making a lot of what?
I'm saying you're always promising that we get to.
I know.
You're making a lot of promises.
Trust the process, sir. Don't worry, we're only on slide 37 of 44. That means the end is near. Then you can come up for air. Oh, we get a chance to practice right here. Isn't that awesome? Let's go to the randomizer here. Pull a name out. Let's see, Tuadros. Can you please tell us what number 1 is right here? You are muted, sir. Oh, yeah, too many speakers on. What was that? Sorry, I'm having a hard time understanding with the echo. I don't have the best hearing. Can you type it in chat real quick?
All right.
I think you have 2 devices picking it up. LC, you are in the right neighborhood, sir. So it is a fiber optic connector. Lorraine, can you help out? You're mute. Your microphone is muted again.
Can you hear me now?
Yes, ma'am.
Is that a fiber optic square tip connector?
That is a square tip, ST. But it is fiber optic, yes. So we got our ST.
I thought ST was straight.
Word. Thank you for catching that failure on my part, SC. Not to confuse everybody.
Got your back, bro.
I appreciate it. SC, square connector. I'm tired too. It's been a lot of talking today. Getting a little lightheaded up here. All right. So SC, number 2, which is down here on the bottom.
Yes.
See what we got here. Sibley, can you please tell us what number 2 is on the bottom left down here? Sibley, can you tell us?
Number 2.
Number 2, right down here.
BNC.
That is absolutely correct on the connector. Can you tell us what type of wire this is?
I'm not sure. They're saying 10 BNC.
So 10-base-2 would be the technical name for it, but I'm not going to hold you to that. I promise you, I'm not going to hold you to that. No, it is a coaxial. So it's like a cable connector, like you would have for cable internet at your house.
Oh, okay.
But you are absolutely correct. That is a BNC connector. Nice work. Number 3, Glean.
That would be a RJ connector, or
little more specific.
RJ11.
There you go. RJ11. Where would we see this? What would be that type of cabling standard?
Mainly for it's old now, but for phone lines, some dial-in modems, or modems in general.
What is the standard we use for that family of wires?
The twisted pair.
There you go. So UTP, unshielded twisted pair.
Unshielded twisted.
So UTP, unshielded twisted pair. Very good. Number 4. Hunter, can you please let us know what number 4 is, sir?
I guess that's the straight tip connector.
That would be the straight tip connector. So we get our
Lucid connector.
A11. So this is the ST. or straight tip. It has the protruding cladding for the fiber optic, and it uses a BNC type connector. So straight tip, ST, straight tip. Number 5 up here at the top. I'm gonna stop throwing the sticks back in, lose track here. Aster, can you please tell us what number 5 is? It's got that L shape up here, kind of looks like a little L.
LC?
LC. So what type of cable would that be on? That is correct. What type of cable would that be on?
No. No, I'm not sure.
Does it use electricity? Does it use light?
Light.
So what of our types of cable standards use light?
Optic.
Here we go. Fiber
Leather?
optic. Fiber optic. There you go. Fiber optic. All right. Bonus points if you can get what LC stands for. Getting a lot of help in chat.
Lucent connector?
There you go. Lucent connector, LC, lucent connector. So LC. So the difference between the square connector, because they're both square. So the LC has a little tab attached to it. Looks like a little L versus the square connector that has just got a little box. I always got these two mixed up. I mean, very consistently, these two always trip me up, the SC versus the LC. Because I knew they both had to be square, but it just, I couldn't distinguish the two for some reason. So this one always tripped me up. So that's good. Lastly, number 6, Jerusalem. Can you please tell me what number 6 is, please?
That is an RJ45.
That is an RJ45. What type of cabling would we see that on?
Ethernet.
Ethernet. What is the term we would use for it?
Ethernet.
Close.
Oh.
Getting some help in chat.
Is it a coax?
Not a coax.
So what's the question again?
What type of cable would it be? So you said Ethernet, yes, which technically, yes, it does fall into Ethernet, but we use another term for it. Wires kind of wrapped around each other.
The Lucent?
No, not a Lucent. So the wires are kind of wrapped around together, and then they're kind of paired up with each other by color.
I'm not sure.
All right, it's unshielded twisted pair. So UTP, unshielded twisted pair.
Okay.
So but very good, RJ45 connector. Excellent. All right, now we get down to it. Network cable tools. We've seen some of these before. We're just going to quickly go over them again. You have the crimper connector. This is how you would crimp the tips on your cables onto the wires. You would feed the wires in the proper order. You would use a crimper. You would insert it in the crimper. clamp it down. There's a little piece in here that will push the wires up, and these metal blades will pierce into the plastic and touch the copper, allowing for that communication to take place. So the crimper can do either RJ45, which is this one over here. It's a much wider one. And they also have a port for an RJ11 right here. So this crimper could actually do either. It also has a cable stripper and cutter in one over here as well. So you would use a crimper connector for the cables themselves. Now, if you're creating the ports, like in the wall or on your punch down block or on your, not your switch, but your horizontal runs in the walls, you would use what is called a punch down tool. I have a video for the punch down tool. I will show you guys probably tomorrow. It's about 4 or 5 minutes. And what it is you have to line these wires up inside the little connector itself. And then this connector or this little piece here has like, it's hard to see at this angle. So I'm going to use some absolutely terrible drawings. So it has like a little U shape right here. One side is flat, goes up like this, and the other side actually has a knife on it. So it has a little blade. So what it's going to do is one side is going to push the wire down. The other side is actually going to cut that wire off so that it cleans up that connector. So you got to make sure you have this lined up properly so you don't cut off the wrong side. So this would be a punch down tool used to create your actual ports or connectors inside the wall. Crimper is used for the cables themselves. So here is showing the use of the punch down. So where one side, the flat side would be on this inside, pushing the wire down. The knife side would be on the outside to cut it off flat so that it looks clean. But again, I have a video tomorrow I'll show you where it shows somebody actually putting one of these together. Questions so far? I'm not sure what you're asking about 6P, Melinda.
It was on the crimper.
What about on the crimper?
It was on the crimper on the page before this one. You see where it says 6P?
Oh, it's 6P. I guess that's for 6 and 8 point. I don't know. I don't know where the 6P is for. I just know that would be for an RJ11 connector versus an RJ45 connector. All right. Multimeter on network cabling and stuff like that. That'll help you to determine continuity as a signal actually going through that line. In an extreme case, you can use it to test a cable, but that's going to be a very long day. If you do that, they actually have cable testers, which will cycle through the cable itself, makes life a lot easier. And then you have a toner probe where you can plug in to, say, one outlet, essentially, then go into the server room and you run that probe along the patch panel, and you can see where it comes out in the wall. Whenever that tone, though, goes into a switch, the switch eats the tone. You can't figure it out at that point. So you have to figure it out at the patch panel. So like if you're putting it in a port in the office, you have to go across the floor to 5 or 6 rooms over. So you don't have to go crawling through and trace the cable all the way yourself. You can use this toner probe to go into the server room, and then test each port on the patch panel, and it will tell you which one is the correct one for the outlet you're having problems with. So that is a toner probe. Does anybody remember what the other name for a toner probe is? What is the other thing it's called?
Fox and Hound.
Fox and Hound. Very good. All right. So here is a loop back plug. Well, we can do this pretty easily with a software, but all the loop back plug does is it takes your outgoing port connectors on that RJ45 connector and loops them right back into your inbounds. So all the loop back does is you plug it into the outside of the computer and you see the light flashing, and that's just a quick way of saying, yep, my NIC is functioning. So my NIC is working, it's sending and receiving signals. I know it's not that. So it's just a quick test. Rarely is it used today, but it's not a bad one just to have in your toolbox for just a quick check. And then over here, we have the cable tester. These two pieces will separate, and you plug the cable into one end of this and then the other, and it will send a tone down each individual wire. And it will tell you if your cable is wired properly, or if there's a break in the cable, or if there's a crossover, like there's some crosstalk going on where, like, if it sends a signal down cable 2 and cable 4 are picking it up, then there's some crosstalk happening. So the cable tester will tell you these things. And again, these are relatively inexpensive tools. You can pick up like this cable tester right here. This exact model you can probably pick up for 10, 12 bucks if you wanted to have something like that. So it's a relatively inexpensive tool. However, predominantly your employer will provide the tools for you that you need, predominantly. Questions so far? Man, we're only 2 slides away. Anybody excited? But we have to get into another little topic here real quick, because
hey, it says optional.
I know it's optional, but we need to know it. You know why we need to know? Because Julian asked the question, and I want to make sure that I don't leave him going, man, I wish he would have told me more. So why do we have 2 standards of cables? So you have your T568A and T568B. Now, if you have a, do what?
Don't put that on me.
So you have the T568A and the T568B. If we have A on both sides of the cable, so if I have an A on this side and an A on this side, that is called a straight through cable. So what is true on one side is true on the other. It is the exact same connections. Now, what this means is I can connect this to the wall, or my computer to a switch, and it is able to now communicate. That is a straight through cable. Problem is, if I try to connect one computer to another computer, they can't talk. Because what's happening is the outbound connectors on one computer is trying to talk to the outbound connectors of another computer. So how do we get around this? We create what is called a crossover, which converts from 568A to 568B. So the outbound connections of one will go to the inbound connections of another. So if I want to connect 2 computers together, I need a crossover cable. And that is the reason for the 2 different standards. Now, if some of you remember back in the dark days of consoles, when the Xbox first came out, they had a really fancy cable that you could buy for $50 or $40. So you could connect 2 Xboxes together and link them and play against each other on like Halo or what have you. That really fancy Microsoft cable that they were selling you, all it was a crossover cable with a really high price tag. So the advantage of a crossover cable allows me to direct connect 2 computers together. So I can connect my computer to my wife's computer, or I could connect one switch to another switch so that those switches can communicate. Now, in the real world, crossover cables now also cross over the blues and the browns, because we now use all 8 pins. Back at the time this was going, we typically only used the 4. So you only crossed over 4 of them. Now they actually cross over all 8. Don't need to know that for the A+. That is more of a real world scenario issue. It's possible you've seen this one, Julian, before. So straight through cable, the standard is the same on both sides. Crossover, one side is 568A, one side is 568B. Questions so far? All right. Yes, this time. You're muted, sir. I can't hear you.
Oh. Can you hear me now?
Yes, sir.
Could you go back to again? Let me see the diagram in the bottom 1 to 7, 8. Yeah, I'll takes to cross over to until 6, but at 7 and 8, there is no connected. Why?
Yeah, 4, 6, 7, and 8 don't cross over at this time because there's no communication going down those lines. They're typically using 1, 2, was it 1, 2, 3, and 6. Those are your communication pins. Now they use all 8. So now they actually, there's a lot more to a crossover than just this. At this time, with regards to CompTIA A+, only 1, 2, 3, and 6 are crossed over. Because they only used 4 lines for, or 4 pins for communication. 2 out, 2 in. Mm-hmm. All right. So with this, we should now be able to define a network and give examples of networks. Rings, buses, stars, mesh, hybrid. Should be able to identify devices used in the networks: hubs, routers, switches, bridges, gateways, firewalls. We should be able to identify types of network cables and connectors: RJ45, F-type, BNC, RJ11, LC, ST, SC, MTRJ. And recognize the most common network tools.